So I guess we'll be starting. So it's my distinct pleasure to introduce Dr. James Evans, who is the director of the Knowledge Lab and professor of sociology at the University of Chicago. He has a PhD and a master's degree from Stanford in anthropology and a BA in anthropology from Brigham Young University. And you may be wondering why a computing research institute is hosting a sociologist. I think you will know soon enough. So he's going to be talking to us today about the embeddings for science and society. So without further ado, please take it away.
Thank you, Kareem, for letting me join you. We had Kareem speak at our institute, our center, last week, and he shared his exciting work on stances and dialects in Arabic. I'm delighted to be here. So just a little tiny bit of background on me. I run a computational social science center here at the University of Chicago that's joint between computer science and the social sciences and economics, sociology, political science, history, etc. And one of the things that I'm struck by in the sciences, as also the social sciences, is how they're just deluged by big text network and other structured and unstructured data, which comes increasingly from high throughput observatories, from the digitization of high throughput archives, from the fielding of high throughput experiments, both natural experiments, which are based on platforms, etc. And one of the things why I'm going to be focusing on embeddings today is because they provide a unique opportunity not only to render high dimensional data in ways that preserves its intrinsic properties, but it facilitates massive integration between diverse data sources, and in particular between structured and unstructured data. So how do we explore the complex relationship between language, networks, transactions, and other structured data? If we want to discover, not assume those relationships, we need to analyze them in the same register. And so we can do what's typically been done, at least in the social sciences, look at them as discrete topologies, or we can think of them as cultural, social, and behavioral fields, continuous fields in continuous complex geometries. So that's what I'm really going to be focusing on today, is several examples of doing this for language, behavior, networks, linking them all together in a variety of different ways. I also, as Kareem mentioned, run a center called Knowledge Lab, which is focused on taking big data, machine learning, and intelligent crowdsourcing, and by that I mean interactive or adaptive learning. So you're only asking the optimal questions that will give you the optimal marginal information from a respondent, to represent knowledge at large scales, to understand it, and by this I mean do kind of a big data science studies, understand the biases and heuristics through which it's generated, and then to transform it, transform the process, for example, of science and scholarship by using those heuristics as statistical instruments to drive future discovery. And we've been using these intuitions to drive discussions about these issues in science. So this was a review on the science of science that myself and colleagues put together last year, as also a number of position pieces. This was another piece from last year on the degree to which the scientific frontier is crowded. My particular view of the scientific space is that science and technology form a complex system. I also am a researcher at the Santa Fe Institute, where we focus on the analysis of complex interaction and complex systems. In this view, there are multiple components which are tightly coupled, leading to emergent phenomena, which involve, in science, collective certainties about entities, forces, theories, black box components in technology, and broad, widespread assumptions in social life more broadly. And so I spend a lot of my time thinking about how to measure knowledge and culture in precise ways. So I'm going to start off with a view of worldviews, one of the things that we might want to capture from the social relationships, behavior, language is we might be interested in capturing and understanding how it is that individuals see the world. And by this, I mean shared meaning structures, which involve behind them different objectives, needs, and purposes of individuals, but also the act of sharing and communicating meaning. So this involves, of course, the degree to which these are shared, the degree to which these represent shared meaning, and then finally structures. So as I mentioned, structures, we're going to talk about those in terms of continuous spaces. In language, in terms of continuous meaning spaces. This harkens back to a long tradition in linguistics. J.R. Firth stated, "You shall know a word by the company it keeps." And Wittgenstein, before that, in the 1920s, talked about, for a large class of cases, the employment of the word meaning, though not all, this way can be explained in this way: the meaning of a word is its use in language. So overlapping contexts provide and construct quasi-continuous metrics between meanings. Such as this, what can be inferred from a bottle of Tesseguino is on the table. If you don't know what Tesseguino is, everybody likes Tesseguino. Tesseguino makes you drunk. We make Tesseguino out of corn, right? So this idea of continuous meanings was brought back more forcefully in the 1970s by a psychologist named Charles Osgood, in which he was trying to measure the connotations of words in context by plotting them on arbitrary dimensions. So for example, he would ask questions like, how does the word pacifist sit in the dimension between kind and cruel? And what he found was that there were high stabilities for different groups of individuals who would plot, for example, words like polite here on dimensions of angular, rounded, weak and strong, rough and smooth. So polite is smoother than it is rough. It's more active than it is passive. It's more good than it is bad. It's more relaxed than it is tense. And it's more fresh than it is stale. But different words, like eager and burning, have different connotations. I mean, they share a connotation of both being strong and both being active, but burning is way hotter than it is cold, and eager is much more fresh than it is stale, and burning is much more dry than it is wet, etc. So these deep connotations he assessed initially through analysis of the underlying principal components of this work. And so what they did was they would use initially work that evolved into using singular value decomposition of word context matrices. And so initially this work was done by taking a large matrix of words by documents. So there might be 20,000 words by, say, 50,000 documents. And you would basically take the principal components of that, but you can't do that in a square matrix. You can take the singular values of a rectangular matrix, and you can use this to plot each word in this singular value space. And this was initially used, for example, for navigation in Google's early search engines. You could type LSI for latent semantic indexing, colon, and then your search would generalize the results not only to the association with the words that you queried, but also generalizations of those words, which is to say words that showed up under the same singular values with the same loadings as the words that you initially stated your query. So the underlying idea here is that we have words and we have contexts, and we're engaging in a factorization strategy that allows us to identify some low number of dimensions, k dimensions, in which those words can be plotted and those contexts can be plotted. And it turns out that Neural networks have exploded this strategy and have facilitated a large-scale heuristic optimization of this factorization strategy. So this is today performed by autoencoders most efficiently. So the autoencoder, and I'm guessing that most are familiar with it, is a device where you've got an empirical input through some deep model ends up producing some encoded representation that then is decoded to predict various aspects of the initial encoding. So you can do this with words, you can do this with images. So if you have 200 images or 2,000 images of Trump, then you can build some underlying embedded code that produces a continuous space along which you could produce any arbitrary number of images, including deep fakes. This doesn't have to be extremely deep. These autoencoders can be relatively shallow. And the first ones that we'll talk about today, the word-to-vec family of word vector autoencoders are shallow. They're shallow logistic regressions in which what's being predicted are masked or hidden words. And so the idea is you have this first L1 layer, a hot one layer, which includes the presence of a focal word and surrounding words. Those are projected to some low number of dimensions, where the number of dimensions is far fewer than the number of words in the vocabulary, typically 1 to 700. And then you predict the words in context or the focal word. So there are really two underlying models of this shallow word-to-vec autoencoder. One is the skipgram model, in which you have an initial word and all of the words surrounding it in some word window. And then what you're doing is you're encoding that into some lower number of dimensions, 100 to 300. And then you're, given that word, you're predicting the appropriate context words with negative sampling, right? So you're basically giving it words that are appropriate context words and words which are inappropriate, right? Random pairs of words. You're training it positively and negatively on those two things through this the factorization strategy that I was describing before, and producing an optimal projection layer. The second of the word-to-vec models is just the inverse of the first. It's the continuous bag of words model, and you take the word contexts surrounding a given word, and given that context, you're trying to predict the masked word in question, right? And so how does one identify dimensions in these spaces? Well, through cross-validation, through just minimizing the loss of the autoencoder, which is trying to predict qualities of those initial words. In this case, it's trying to predict accurately the context words, if it's the skipgram model, or the focal word, if it's the SIBO model, the continuous bag of words model. And now, just a few notes on the math of high dimensional spaces. Even though these encodings are low dimensional with respect to the number of words, they're high dimensional with respect to the way in which we intuitively think about low dimensional geometry, which is to say geometry in 2 or 3 dimensions. So there are a few notes to think about when we start interpreting these word and context dimensions. So the first is that as you shift from a low dimensional sphere to a high dimensional sphere, almost all of the volume is near the surface, right? So the idea is most of the volume of some d-dimensional ball of radius r is contained within the annulus of width ORD near the surface. So as a polytope moves to infinite dimensions, its volume goes to 0 and its surface area goes to infinity. So in the end, everything is on the skin of this surface. And what this means is that rather than using Euclidean distance, which assumes a volume inside that polytope or that sphere, rather you want to look at the angle or the angular distance between things on this skin. And this also naturally normalizes for length of things like document. Second aspect of high dimensional.
So if I may interrupt here with a question.
Sure, of course.
So the greater I mean, if you go to much lower dimensions, then you're kind of losing information. If you go to very, very high dimensions, then you have a lot of capacity, but you're over-representing the language. So where is the appropriate point?
Like I said, typically we do it. We identify it through cross-validation, and for regular natural language corpora from a singular domain like news or like expository documents like in Wikipedia, we found that between 300 and 400 dimensions are appropriate. On the other hand, when I've just embedded keywords, for example, from a given domain, then it typically requires 1/10 as many dimensions. And if I'm using a different geometry, as I'll mention a little bit later. So, for example, this is assuming a Euclidean geometry. If I assume a hyperbolic geometry, which allows a bridging structure, so it allows basically the presence of sparsity in the network, then I can typically represent in about 1/10 of the dimensions that I might otherwise represent it in. So rather than 300, I can get the same purchase with 30 dimensions. Still high dimensions with respect to this. So angular distance still makes sense, but you actually, typically you don't, there's not a problem by overshooting the number of appropriate dimensions. You're just not using all of the capacity or the space that you otherwise were given access to. So I think that the downside for having too many dimensions is small, and so typically people will take an upper bound number of dimensions to estimate their work, unless unless shrink wrapping the dimensionalized space is critical for other reasons. Does that make sense?
Yes, it does.
Okay.
Thank you.
Sure. So the next property of high dimensional geometry is that two random points from d-dimensional Gaussian with unit variance in each direction are approximately orthogonal, which means the entailment of this is that right angles in a high dimensional space represent random alignment. So if two things are at 90 degrees from one another, that means they have no association with one another within the space. If the angle is greater or less than 90, that means they have a non-trivial association with one another inside that space. The third is random projection. So at least when I was in school as a kind of complex systems network analyst, I was taught that really the geometry of networks was uninteresting to examine, because if you had n nodes in the network, then it would require n-1 dimensions to represent them without distortion. And while that may technically be true, it turns out there is this powerful John and Lindenstrauss lemma from 1982, which shows that you can represent them, that the upper bound is closer to log n, and that's an upper bound. It's typically much less with only epsilon distortion. So for a tiny amount of distortion. So this is really the theorem that makes it possible to embed these complex topologies in geometries that reveal underlying structure. So what can we do with these spaces in the context of words? Well, we can identify how semantic relationships induce systematic semantic shifts. So man to woman, uncle to aunt, king to queen, all shift in the same direction implying an underlying gender dimension. King to queen, king to kings, queen to queens, shift in another underlying dimension that represents plurality. And so what we're going to try to do through large-scale document corpora is to grow a kind of culturally appropriate brain. I think this slide is not coming through. Anyway, I'll just tell you what it says. We're going to draw a kind of a semantically or culturally appropriate brain through stories. So every time there's an expression like he carried his tuba or she dropped her flute, then tuba moves a little closer to he and flute moves a little closer to she. Or Steve's pickup truck skidded to a halt, or get out of the minivan, ma'am. Minivan moves closer to ma'am, which moves closer to woman. And Steve moves closer to pickup, moves closer to man. So we basically have this association between these entities. So I'm gonna give a few examples of how this works. So one is a recent project in which we analyzed how different languages suggest different kind of semantic structures or semantic brains. So we took large-scale corpora, so the Wikipedia from a number of different languages, from 35 languages, and we also took TOEFL exams. So these, for anyone who studied in the United States, these are 250 word essays on specific exam questions, essay responses. And what we found was that there were high or strong associations between the embeddings for the English language essays for people whose initial language was the same and for their initial language, right? So the embedding for semantic associations, so for word vectors, for someone in Greece, right? So in Greek, from Wikipedia articles that were written in Greek, ends up bearing strong similarities to the English language essays written by Greek speakers. And the same is true for Arabic, right? So there are strong associations between the structure of Arabic from Arabic Wikipedia articles, and then also for English language essays, which are written by Arabic speakers. And this is true not only for like poor English language essays, like low scoring essays, but also high scoring essays. Now, in the past, people who've looked at lexical semantics across languages have argued that people have universal empirical or concrete experiences with the world, with mountains and air and water, and that should lead to universal semantic spaces. And it does turn out that when we cluster words as a function of their loadings on these underlying 300 dimensions that we kind of embed them into, we do find that these embedded clusters end up being highly associated with the concreteness of the words in those clusters. And so one of the things that we did first was to identify, well, how similar are the position of concrete and abstract words across languages with respect to one another. And we do find that more concreteness is associated with a greater similarity across languages. Nevertheless, even those extremely concrete words like ash, cloud, day, earth, and fire end up shifting as a function of the distance in meters of the languages in question. So the further you are from the focal language, even the most concrete words end up deviating as a function of that distance. Moreover, when we look at underlying properties of that distance, like the climatic distance between two places, the grammatical distance, the lexical distance, the cultural or physical distance, or even if we dive in very specifically into aspects of culture like kinship, possession structure, basic technologies, religion and beliefs, we find that basically word distances vary as a function of these things in really powerful ways. So for example, kinship structure ends up being the strongest predictor of the likelihood that two sets of language word meanings align, followed by possession. So these are kind of like legal norms of possession, etc. And similarly with respect to lexical and grammatical distance, these affect the alignment. But it turns out that these aren't the things that characterize them the most. In a paper that's under second review at Nature right now, we show that the thing that characterizes the difference in lexical semantics between languages is local similarity and global variability. And so what we mean by this is that clusters, like for example, the one that you can see here, the cluster for music, so instrument, guitar, album, composer, song, solo, these are highly conserved across languages, as are spiritual, deity, sect, sacred, monk, as are, army, officer, battery, command, guard, attack, right? So basically, local clusters of words are highly conserved across languages. What's not conserved is the global association of those local clusters. And it turns out it doesn't matter what cluster solution we selected. In fact, as we pick more clusters, the difference between those local and global associations diverge. What this means is that there are a space of available metaphors in one language that are different from another. When people are making analogies, making metaphors, articulating similes, or answering TOEFL essays, the space of proximity of these semantic clusters suggests what to say next. And so we can show how these vary by language. Some of them are more shared. So for example, these associations are pretty intensively shared, which is to say, that time is central and is attached to things like performances and governments like democracies and ideas like belief. But most others are not shared. They're only shared by specific languages. So for example, the relationship between army and disaster is characteristic of languages like Indonesian, Portuguese, Romanian, Spanish, and Telugu, whereas the relationship between messages and music is characteristic only of Gujarati and Indonesian, or even rarer associations like that between democracy and performance in Tagalog versus music and spiritual agents in English and Farsi, or even rarer ones which are single language dependent, like the association between time and chemicals in Dutch, or between plants and injustice in Nepalese. So one can also, do more than just build clusters around semantic spaces, but we can also identify underlying semantic dimensions in different languages, but also different times and places. So, for example, we could take a dimension like the dimension of class, the difference between someone who's rich and poor, between the words richer and poor, affluence and poverty, expensive and inexpensive, all of these dimensions, which are constructed literally by taking the word vector for rich and subtracting the word vector for poor. It turns out you can also divide by the word vector for poor. These are highly correlated with one another, and if you average them together, they form a robust semantic dimension associated with affluence. From that dimension, you can project all other words onto that space. So this is actually real language data in English. So for example, these are sports. So golf is a rich sport, camping and boxing are poor sports. Hockey, baseball, and basketball are in the center. And moreover, you can project things to multiple dimensions, right? So these are projections onto the gender and the class dimensions simultaneously. So this allows us to interpret the proximities of these spaces in a powerful way. For example, you can identify the associations between class and politics in United States language. So you can see, things like golf and steak tend to be both conservative and rich. Union is both poor and liberal, but everything fills out. Subaru and a latte is liberal on the one hand and rich on the other. Evangelical, rancher are conservative and pickup and evangelical are conservative and poor in this space. So we actually tried to validate these by asking individuals whether or not these associations matched with their own personal sensibilities. And so we just asked them, for example, how would you rank tennis in terms of its masculinity or femininity, its high class or low classness, or the degree to which it ranks on some other kind of racial association. And we found a strong association between these Mechanical Turk surveyed responses and contemporary embeddings. So embeddings that were generated at the same time as those survey responses. So you can see, hip hop and rap are in the same relative location: jazz, opera, techno, bluegrass, etc. So basically, these are conformal associations. So angle preserving associations. And it turns out that, when you look at this across dimensions, you can either just, take the average of those dimensions, as we did in semantic space, and predict. It turns out that our semantic associations predict about 87% of the surveyed responses to the gender, for example, of different objects. If we actually re-weight those dimensions according to those that most describe the survey responses, we predict about 93% of the overall variance in associations inside people's heads. Moreover, we found that we were able to do similar things if we took 1950s era text. We could predict 1950s era associations from surveys that were performed by Osgood's students, basically, by people who were interested in these semantic differentials and doing public opinion surveys at the time. As social scientists, we have we also want to test the robustness and strength of these associations, and so we can do non-parametric statistical inference by seeing their robustness to removing specific documents, to making sure that they're robust to outliers. And so we can do this either by building Bootstrap error bounds, by building basically semantic spaces that are drawn on a Bootstrap sample of underlying documents, or if the embeddings are sufficiently computationally intensive, then we can build subsample error bounds by just building a random partition of, if we want a 90% error bound, 20 partitions. Then we build these functions, as I can show here, over the second and the 19th order statistic, which might be a closeness or it might be a projection to one of those underlying semantic dimensions. And that allows us to talk about their statistical significance or their solidity or robustness with respect to individual documents. So you can see, if we're looking at these over historical time, that engineer, journalist, and nurse shift really significantly on the gender dimension. When I say significantly, I just mean it's not accounted for by any particular subset of documents. They shift on the class dimension, and you can see a shifting association between gender and class over the same period, right? The angle moves towards no angle, right? Or between a 90 degree angle, which is basically no association or random association. So actually at the turn of the 20th century, what you find are, at the turn of the 19th century, that femininity was strongly associated with class in England and the US, and then those become unrelated basically in the 1970s when the divorce rate and participation in the labor force becomes approximately equal. One of the things that you can see if you look at many dimensions that are related, is their remarkable stability over time, right? So we can look at education, the cultivation aspect of status. We can look at morality, employment, and gender. And each of these are highly stably associated with affluence over time. Moreover, we can use these word embeddings to embed our intuitions. So we can actually take, in this case, all of the sociological literature on class and embed it and its associations over time and see what's identified similarly and differently from actually what in contemporary culture was rendered. And for the most part, there's a similarity. So there's a strong association or an attention to education, which we can see here. So there is a growing association with education and affluence, which is rendered in the literature. But other things are artifacts. So for example, there's a growing attention to the cultivational aspects of affluence, which turns out have always been there. And in fact, we can identify the things that were missed basically in theory by mapping onto one another the two projections, right? The projection in the corpus that comprises how it is that people have thought about class academically, and the corpus of how it is that people in the world have talked about class. A couple of other observations. One is, as Kareem was mentioning earlier, the irreducibility of the irreducible high dimensionality of status forms, right? So even though, for example, employer and cultured are, have like a 73-degree difference, and cultured and status have an 85-degree difference, you can't render that in two dimensions without massively distorting the associations in this space. Even though, these, in this case, the 4 dimensions we look at in this plot are highly correlated. Nevertheless, they end up representing different angles. So for example, employment or being an employer is strongly associated with being rich. Being rich is strongly associated with being moral, but being an employer is not at all associated. In fact, it's negatively associated with being moral in American culture, right? So things that are close together in one dimension, like employer and wealth, are different in another dimension, right? Which is the association, rich and morality are close in another dimension, but employer is far from morality in that other dimension. So adding additional dimensions allows the space to take into account these intransitivities. Every time you have an intransitivity between associations between words, adding another dimension will allow you to resolve that. Moreover, when one looks at these over time, what's interesting is that even though those dimensions are remarkably stable, the word projections, like the individual words that project onto those dimensions and characterize their extent, change dramatically over that period. So this is the association across each decade of the 20th century of the words that correlate to that dimension. And you can see how they drop precipitously and continuously. So on the employer-employee dimension, at the turn of the 20th century, who were those who were employers? Well, earls, governors, mayors, bishops. At the turn of the 21st century, promoters, masters, captains of industry, speculators, moguls. And at the bottom end, from bodied, service, suffering, and soldier, you get effectively replaced by wage, retirement, unemployment, etc. Now,
so if I may, so basically you're capturing societal constructs or social constructs that exist in the world.
Yes.
And the language is kind of, projecting all of this.
That's right. So even though, for example, the way in which we view status, the way in which we view status is remarkably stable over time, but the words that are associated with high and low status are constantly churning and changing. So we're identifying these really large-scale, stable, underlying semantic dimensions, even though they trace dramatic underlying changes. Yeah.
Thank you.
Sure, sure. And, we can also, we can just look at, we took every antonym pair in the language, and you can identify, for example, how these associations, stabilize and change over time. So you can see you've got, gender, maternal, paternal, fashionable, unfashionable, bisexual, homosexual, emotional, cerebral. These allow us to describe this space, and the context matters. For example, these are projections at the turn of the 20th century, so 1900, in the UK and the US on the gender dimension and the class dimension. And so you can see, for example, in England is the most masculine, and the US is quite feminine. Colonies are extremely feminine or feminized. Whereas in the US, the USA is the most masculine, and colonies as a concept are highly masculine. Similarly, in the United States, wilderness is elevated in its class or status projection, as is farmer, whereas the idea of rank and nobility are much lower in the US context than they are in the UK context. So both time matters, but also the perspective of the individual who's observing this matters. And there are many other things you can do. For example, if you're in a particular place, then ideas which are close or relevant to your space seem far apart because they're close to you. Those that are objectively further from one another, but they're seen from a great distance, end up appearing to be much more similar to one another. So it's almost a cultural theory of relativity that has formal equivalents that are highly predictive. Now, these spaces do require some intuition and some theory to anticipate them. Just, I don't know if anyone's read The Hitchhiker's Guide to the Galaxy, but we thought, hey, we're going to find the one dimension that explains the most variation in all word associations, and it's going to be powerful. It's going to tell us what's, what is the backbone of culture. And it was steroidal minus non-steroidal. Now, it turns out that steroidal and non-steroidal are so close in the space that the angle that they inscribe is effectively arbitrary. But it suggests that these spaces cannot be analyzed in a completely theory-free way. They require some anticipation. A couple of other ways in which one can use these. So if you use Euclidean spaces or Euclidean geometries to embed words and associations, then you get dimensions. But if you use hyperbolic spaces, so these are continuously negatively curved spaces, then you can identify linguistic or network hierarchies, right? Where those that are at the center of the space are closest to everything at the periphery, but those things at the periphery are not close to each other. So you can think about hyperbolic spaces like the fringed edge of something made out of macrame, or a floret of broccoli, or a mountain ridge. Someone on the top of the ridge is close to someone on either side, but those two people on either side are not close to each other. And so I can visualize these, for example, by taking that hyperbolic space and projecting it down to what's called a Poincare disk. And you can see from this kind of cartoon example how it is that things that are at the center versus that are at the periphery end up capturing, things get positioned at the center of the space, which are the most widely connected. And so we see this both in terms of networks, but also language. So we can trace the space of 21st century physics, plotting it to this Poincare disk, which captures the first two of these hyperbolic dimensions. And it allows us to identify and trace how it is that these spaces are moving over time. And one of the things that we find is that centralization in one space, so in the network of collaboration, ends up being highly correlated with centralization in the topic space. So there's topics which end up being most connected to one another over time. And they end up co-predicting each other in a way that reinforces that basically social connection drives or is strongly associated with cultural collapse, or the collapse in the ideas that are explored in a particular space. Another way in which one can think about embeddings are these high-dimensional contextual embeddings. So the most famous of these models was the BERT model, the bidirectional transformer encoders. And so what these methods do, and I don't have time to discuss all the technical details, but I'm happy to talk about them in the Q&A. In what you're doing is you're embedding a set of documents, but you're unleashing an attention mechanism which allows a complex alignment between the encoder, basically, and the decoder. And so these were initially developed in seek-to-seek translation models, and that attention mechanism allows one to dynamically identify which words are associated with any particular word in question, which may be much further afield than just the surrounding 5 or 6 words. This transformer encoder can go both directions, so it predicts missing words from the end of the sentence and from the beginning of the sentence. It also it predicts the next sentence, and so it's really become powerfully used for question answering and for a wide range of semantic tasks. How does one think about words and meanings in these spaces? Well, instead of a word being a vector, a word in these spaces is a point cloud. So, for example, this is work we've done just validating how to use these. So percent, the word, and percent, the sign, end up being, like almost overlapping, as you can see to the left. Virus, activity, and disease some of them are close to one another, some of them are far from one another as a function of their particular usage. So each word in a given context has a given position, okay? You can see across the many channels, the output channels of these models, the positions of different words are highly similar, conserved across these spaces. And this allows us to do things like trace scientific attention in scientific documents and cluster scientific spaces in powerful ways. Moreover, if you align words between communities, you can identify the difference between separate communities because they use the same words in different ways. Moreover, you can use these spaces to do powerful classification. So you can distinguish between, these are the articles in 2 different journals. You can do this much better with a contextual embedder than you can with a simple word embedding. It turns out that there are many complex outputs of these types of models, and these complex outputs end up, you need to pool them, and pooling ends up mattering. And so we've done a number of experiments to identify which pooling strategies work the best. If you don't pool correctly, or if the underlying contextual embedding is not trained on documents that are similar enough to the context that you're interested in, then word embeddings do better than a poorly trained contextual embedder. So my time is largely up. I had several empirical examples. Maybe I'll just literally it'll be like a montage. I'll just mention a couple and then I'll open it up for broader questions. So we were interested in understanding how it is that individuals collaborate. So one of the things that we did to do this was built a model of how people contribute to Wikipedia pages, and then look at the diversity of political opinions in the construction of Wikipedia pages and its influence on quality. And what we find is that the greater diversity is strongly associated with higher quality pages. So, so diversity matters. To make sense of this, we went into the talk pages underlying the Wikipedia page construction. So every time you're going to add a new thing to a Wikipedia page, you have to argue on behalf of that inclusion or exclusion if you're going to remove something in the talk page. We embedded these talk pages in an embedding space which was described or trained on all of Wikipedia. And this allowed us to show, for example, that, that greater polarization was associated with fewer semantic topics. So the polarization was political. People who would argue, they would talk more about political topics, but they would talk about those topics in more ways. So there was a 25% increase in the lexical diversity, the TF-IDF characterization of the words in those spaces. So this is just one example of how you can kind of control and normalize for diversity and semantic extent. Another thing that we analyzed is how it is that science as a system thinks. And so does it deduce, does it induce, or does it abduce? Does it basically get surprised and generate hypotheses as a function of that surprise? It turns out, so we basically take every article and every patent, we embed the hypergraph of those patents. So an article might contain a set of keywords, or a patent might contain a set of technical codes. We embed the hypergraphs, or the hypergraph, each hyperedge being a paper or patent, in one of these embedding spaces, and are able to use these to predict next year's papers and patents. So we can predict about 98% of next year's papers and patents. The thing that's the most interesting is that surprise. So the least predictable paper or patent that shows up in the next period, that unpredictability under this most predictive model itself predicts like 60% of the likelihood of being in the top 10% of citations or attention. So systems of science and technology are really driven by abduction. They're driven by surprise. And so you can see this association of content and context novelty that drives the probability of hits, which is the likelihood of being in that top 10% in the biological sciences, the physical sciences, and patents. What's more, where do these discoveries come from? They come from aliens. So they come from not from unusual people, unusual careers, or from unusual teams with unusual expertise. They come from groups of people with a given expertise that travel across the scientific space to another area and solve that area's problems, publishing in their journal, in a journal that's never seen people like them before, and no people like them have ever traveled to these problems before. A final example, I'm just going to mention it. This was a paper in Nature that we did not publish, someone else published, that predicted new properties of materials as a function of their embedding in an embedding space close to the name of those properties. So thermoelectricity, for example, might be imputed to have this kind of copper compound that you see in the upper right might be imputed to have this thermoelectric property if they're close in the embedding space. And they were able to predict about 40% of the likelihood that any given chemical would have that property as a function of this proximity in space. We thought it would be important to take into account the people who are making those inferences. And so we decided to embed people and text at the same time by building random walks through authors and materials across all these papers. And we were able to double those predictions from 40% to 85%, or in the context of ferroelectricity to 83%, in the context of photovoltaic capacity, 92%. So we're able to dramatically increase our ability to predict these spaces as a function of taking into account multiple registers, people as well as the availability and connection between their properties. So I'm not going to give other examples of embeddings. I'll just I'll close and open it up for your questions.
Thank you so much for an interesting talk. So we'll open the door for questions. There's a tab for Q&A on the side. So feel free to ask any of your questions here. Until we get questions, I was wondering what is the most interesting, association that you found in the work that you were doing? Thing that you didn't really expect to see.
That's a good question. Let me think. Well, I think one thing that was surprising to us was in the cultural work earlier. We expected. So if you look at the sociological embedding, there's a strong association between masculinity and wealth, because men have the wealth. But if you actually look at the cultural representation at the same period as the turn of the 20th century, it's exactly the opposite. So femininity is associated with wealth, and if you look at the words that drive that association, it's because basically at the turn of the 20th century, women were like mannequins of conspicuous consumption. So jewels, furs, etc. And so this kind of this is the shift in these cultural association, that gender association was not one that we anticipated, and yet it kind of really powerfully described changes in the family structure and in the social structure over that period in a way that we hadn't anticipated.
Okay, there's a question here. It says, is the affluence data based on American sources only, or do you have other sources?
Yeah, the texts are American texts, and the affluence sources American affluence. If we were interested in, we've also done it for English language, for English texts, German texts, etc., and we find a dose-response relationship between these cultures. So, for example, if there's a stronger gender association, like in the gendered conjugation of verbs, for example, or the gendering of nouns in different languages, that ends up being associated with individuals' gender associations in those very languages. And the same is true for veridical associations between, for example, women participation in certain occupations and the embedding of words in a gender, the embedding of occupation words in a gender space.
Okay, we have a couple more questions. As we have vector-based shifts for masculine to feminine or singular to plural, is there a space where we could have a vector-based translation from one language to another? I guess this is like the sec-to-sec models, I guess, that you referred to at some point in time.
Yeah. Well, I think this has been the power of these contextual models. So you certainly can do that. We've been doing a couple of things with these, where you take two languages, and you can build an embedding model that links embedding 1 to embedding 2, that optimally aligns these two embeddings. And one of the things that we've been playing with here is identifying the optimal rotation reflection shift. So if you align two embeddings, you can also see if you were to reflect or to flip associations, how would that maximize the alignment? And it basically suggests the areas in which these two language cultures conflict with one another directly. And it turns out that if you do that, you can the number of reflections actually predicts the conflicts that those people will have in conversation. So we've been looking at, for example, like in Reddit forums, people talking about different subjects, and we can predict the likelihood that they're going to disagree about a subject as a function of these misalignments, basically, between spaces.
Okay, so we have a few more questions here, and the questions keep coming. So there's a question about, is there a way to perform any counterfactual or causal analysis on shifts?
Just because we don't have a lot of, if we were in an interactive space, I would ask, there are many causal questions that one might want to ask. I think this is one of the things that we were trying to do with our analysis of the shift in education and in its association with wealth and cultivation over time. So one can certainly do Granger causal associations, which are basically, what's the relative likelihood that you're going to engage in a prediction. You can also use, if you're familiar with this approach, the deconfounder approach that was basically, published by David Bly in the Journal of the American Statistical Association last October, which basically allows you to identify, it's called the paper is called The Blessings of Multiple Causes. And it allows you to look at how it is that different independent variables, how they vary, ends up suggesting an unmeasured confounder variable. And so if you have a number of different potential predictors of a change, for example, in cultural association, like if women are entering the workforce, women are getting higher levels of education, and one might assume that that's going to predict a change in cultural association of women with respect to other cultural tropes over time, then one can do a deconfounder approach to see how it is that these independent movements end up influencing this outcome. And yet, at the same time, I would caution the fact that these cultural associations are almost invariably cause and effect. And so there's a complex causal husk that I think is very challenging to really unravel, because obviously women entering the educational space is partly associated with changing cultural associations of women. And so I think precise causal identification is going to be difficult for cultural associations, because they're both manifestations of behavioral change as well as motivators of behavioral change.
Okay, so I guess we'll try to, we have a couple more questions.
Yeah, I've got all the time in the world, so I have no.
Okay, great. So
I'm good.
So the question says, embedding models can be sensitive to hyperparameters used for training. How sensitive are the conclusions that you draw to specific embedding models used and the training hyperparameters?
That's a great question. In these cases, I showed error bounds as a function of whether or not you included particular documents, right? So you can build an embedding with a Bootstrap sample of documents. If you build that Bootstrap sample, so each Bootstrap sample, which is basically, if you have n documents, taking the same n documents but with replacement, any two samples are going to have, on average, a 60% overlap, which means that you're going to throw out many of the. If there's an outlier document that's driving the association, it's going to be in some of the samples, it's not going to be in others. So you can do the same to do a sensitivity analysis for these cultural associations with respect to hyperparameters, like window size and these other things. And all of the associations that I'm describing were sensitive to a wide range of hyperparameter selections. So, but I completely agree. It's important to show, are they consistent across these hyperparameter associations? And if they're not, why not? Yeah.
Very well. So there's a question that says, words have many senses and also have many surface forms. How do you handle that?
With contextual embeddings. So that's where I'm just going to show you this. Sorry, so many things to talk about. And this is, and I know this sounds crazy, but this is just a fraction of the things that we've been playing with embeddings. I mean, there's so many exciting things going on with applications. Okay, so here we go. Okay, so these are, for example, this plot in the principal component 1 and 2 of this 768 dimensional space. So this is a high dimensional space. Each, where it says virus in the middle, each of those points of the word virus are the word virus used in a different context. So if someone said computer virus, that would be different from coronavirus. That would be different from a metaphoric use. This social media is a virus on society or whatever. So all those word senses end up. So the contextual embeddings allow you to disentangle the associations between words and meanings. That's how you can do it with contextual embedding models. If you want to play with word embedding models, the various meanings are basically squeezed into disassociations in the high dimensional space. So that word will be close to some words in one dimension and distant from other words in other dimensions. But it necessarily, and even though that allows many meanings of a single word to be represented polysemously, this is a true representation. But just actually, there's a beautiful paper in 2018 by Rishi Arora, computer scientist at Princeton, that shows that if you arbitrarily take two words in the language and you give them the same token, so XXX, XXX, for both fear and democracy, so that they embed together, it turns out that their position is a linear combination of the two meanings. And that means you can actually disentangle the two meanings. And so there are ways to kind of do high resolution topic modeling by using this intuition and in simple linear algebra to basically disentangle these kind of discourse atoms or meanings in the language space.
Okay, so let's take the next question. It says, how do you keep privacy in the era of big data and the embedding of everything? What's your take?
Okay. This is one of the things that I think I'm the most excited about is that, so I'll give you a simple example. I'm interested in studying, I study science as a system. That's one of the things that I do. And so I am interested in how peer review influences the scientific system, influences the technology system, so the granting of patents, et cetera. But some organizations like Nature, they don't want to give me the reviews of their papers because those are private reviews. They were written privately for Nature. And they certainly don't want to give me the papers that were rejected because of those reviews. That could be subject to a lawsuit. But if I build an embedding, basically, right, that encodes those reviews, that encodes successful and unsuccessful papers, they're able to share these embedding models without sharing this identifying information. So there's no way to recover the underlying structure of data that constructs this underlying embedding model. So these embedding models end up unleashing data that would otherwise be very difficult to combine across institutional, government, and corporate boundaries. And it allows the protection of privacy. So
embeddings are actually are helping privacy, not more privacy, not less.
Much more, yeah. So there's a whole new era of model sharing, which is facilitated through these embeddings.
So we'll go with the last question, and how is this applicable to social media, as these shifts might not be might not be the same as for other types of media like data, books, news articles. So I guess he's trying to ask, how does the shift? I mean, if you have embeddings in the social media space, how does it project in other kind of genres or texts and so forth?
Yeah, that's a great question. So, for example, if you I'll give two examples that are not social media, but then I'll follow with a social media one. We've looked at like Wikipedia, encyclopedic entries on the one hand, and like narrative news on the other, where people are telling stories, and you see much stronger gender associations in the narrative news than you do in Wikipedia, because in the narrative news, people are describing the gendered association of events in the world. A woman driving her minivan, a man driving his pickup truck, a man engaged in programming, a woman who's, ironing, etc. Right? So these gendered associations come out through the replication of stories. They don't come out through expository documents where you're not rendering persons in context. You're taking them out of context. So there's no question that the underlying game that's involved, like the social media game, when you're engaged in social media, you're doing different things than you're doing when you're engaged in, expository Wikipedia writing than you are doing when you're basically sharing narrative news. And so I would expect that these associations would be different in some dimensions that are associated with the particularities of that game, and they allow you to diagnose what's going on in the context of social media. So are people, one of the things, and this is specific to social media, that I found with respect to science is the same with respect to social media. So there have been a number of papers that talk about how it is that fake news spread in social media spreads faster. The thing that they don't explicitly measure, but really accounts for that difference is the same thing that I see in science and technology, which is surprise. Basically, surprising facts are the things that attract the most attention. They're the things that violate people's underlying models in social media and in science and technology. And so, the fakest news ends up making the most sensational claims, which most violate our understandings of the world. So that attention mechanism ends up being highly similar, both in magnitude and in form, in science and technology on the one hand, and in social media on the other. So there are, and that's again because the game that's being played is similar. Actually, people have a worldview; they're trying to update it. As it gets radically updated, that draws attention as people scrutinize these new facts and either incorporate or reject them.
So should we write the most outlandish papers then?
If you want to attract the most attention, either your success or peril. So basically you should write the most outlandish papers conditional on their being replicable.
Okay. Very good. Okay, so I guess we have no more questions, and I would like to thank you very much for giving us your time today and for a very interesting talk. And hopefully we'll connect soon.
Yeah, thank you. And just one note to whoever else is listening here. We're very interested in exploring the utility of these in other contexts, in other language and cultural contexts. And that was the reason I was excited to chat with Kareem and your community, just to learn more about opportunities for collaboration with a group that has developed such powerful language resources for the studying of dialectic Arabic, for example. So please reach out to me if you are interested in talking data and analysis. So okay.
We will. Thank you so much. Have a great day.
Okay. Goodbye.